In this video, we are going to be talking about change of basis. And an analogy I like to use to think about change of basis is different units of measurement. So say you have something that's 1 inch long, you can also say that it's 2.54 centimeters long. And in both cases, you're describing the exact same length. The only difference is the numeric value because you're using a different unit to describe it. And I like this analogy because it shows how it can be easier to describe something in a certain unit of measurement versus in another. Because in general, having like the whole number 1 is much easier for calculations versus having 2.54, which is a decimal value. So this all relates back to change of basis because the motivation behind this technique is being able to simplify calculations. So say you have this bunch of equations, this huge matrix, you will be able to change it into the appropriate basis, which we'll talk about more later on, and then do the calculations in that basis and then change it back. And this is helpful because the calculations will be simpler in that appropriate basis. And something to keep in mind is that the whole bigger picture we're striving towards is being able to solve differential equations of RLC circuits. And it's totally fine if you don't know exactly what this means yet or how to do it, because this video and the next few videos will guide you towards and teach you all the necessary skills in order to do this. Cool, so let's dive into what change of basis really is. So in general, whenever you describe a vector, you usually use the xy plane. And let's say we arbitrarily have the vector 2, 3. So whenever you're describing it with these coordinates, you're describing them in the standard basis. And this basis relies on the two vectors 1, 0 and 0, 1. So based on this, you can see that if you were to describe 2, 3, a way that you can represent it in this basis is taking 2 times the first basis vector plus 3 times the second basis vector. And if you rewrite this in matrix multiplication form or matrix vector multiplication, it would just be 1, 0, 0, 1 times 2, 3. So in this scenario, this matrix is your basis matrix. But notice that in this case, this is just equal to the identity, and that's because you're in the standard basis. So now let's try to examine another basis in order to see how it's different and how you can represent the same vector 2, 3 in another version. So let's just arbitrarily take the basis of where the axes are along the diagonal instead. So in this case, you would have the basis vectors 1, 1 and negative 1, 1. And again, this is just another basis. So it's not a specific basis I'm picking, but just another example. So we have 1, 1 and negative 1, 1. So now here, we can also do the thing where we represent it as a linear combination of the basis vectors. So we ultimately want to get back to 2, 3. But we aren't sure what the coordinates are going to be yet. So let's just call them A and B for now. But keep in mind that we don't know what these values are yet. So we can write it out in the same way with A times the first basis vector plus B times the second basis vector. And same thing, if you rewrite it in matrix vector form, it will result in 1, 1, 1 times AB. Now, if we use these two endpoints, you can solve via Gaussian elimination and get the values of AB. So I'm going to skip that step, but the values you should get are 5 halves and 1 half. So that means in this other basis, the coordinates of this vector are actually 5 halves and 1/2. So the same exact vector is being represented, but since you're looking at it from a different point of view, the coordinate values are different. And an overarching idea to get from this entire thing is that any vector can be represented as a combination, a linear combination of basis vectors. And this means in multiple different bases as well. Because, for example, in the standard basis, it's represented as 2, 3, while in this other basis, it is represented as 5/2, 1/2. And something I also didn't point out earlier is that appropriately, this is the basis matrix in the other basis. So essentially, the basis matrix is always just going to be the basis vectors stacked horizontally from each other. Okay, so now we have an idea of what different bases are and how they are different and give you different values while actually still describing the same thing. Now let's see how you change it from one basis to another. So the kind of golden formula you always want to keep in mind is AXA is going to be equal to B, let's say. And in these cases, AB are basis matrices and XA, let's see, for the coordinates and the appropriate basis. And usually the most common problem you're going to encounter is that you have something in the standard basis, but you want to, say, change it to basis A. So how would you do this? So let's just start from the equation itself. So you have AXA is going to be equal to the standard basis, which, as we said above, the basis matrix is just the identity. So I times the vector SB. Oh, and by the way, this is supposed to be subscript B. Cool. So then in this case, this is just equal to XB, which is how we're representing it in the standard matrices. But you're trying to get to the value in basis A. So now you gotta take the inverse of the matrix on both sides. So you have XB is just equal to A inverse of XB. So this is the usual formula you would want to use in order to go from a standard basis to this other basis A. So in this case, it shows how your change of basis matrix must be invertible. So this is another fact to keep in mind. Cool. So these are the basic ideas of change of basis, but let's dive into an example problem in order to examine it more. So given that V is the change of basis matrix from S coordinates to standard, and this matrix A manipulates X to become Y in this S basis world, we want to describe AS in standard coordinates. So a great way that I like to start out with is just drawing the diagram of what matrix does what and what basis options you have, because it can often get really confusing where you're trying to get and what you already have. So we have normal X, these are vectors, We have normal x, normal y, and I'm saying normal as in terms that they're in the standard basis, and then we also have x in the s basis and y in the s basis. So now we know that V is a change of basis matrix from the s coordinates to standard. So that means that when you multiply the x coordinate value by V, you will get back to the standard. And this happens no matter what vector you multiply in those appropriate bases. So it also happens for the corresponding y's. And if you go somewhere and you want to be able to get back, you should be able to just take the inverse. So in the opposite direction, it will be the inverse. And it also tells you that in order to get from x in the s basis to y in the s basis, you multiply by as. And the ultimate thing that you're trying to find is the same linear operator but in standard coordinates. So it's read a instead. And something that to point out is that here with the change of basis matrices, we included both directions as well. So we included the inverse, but we can't necessarily do that with A and AS because we don't know if it's invertible, and it's actually not really necessary in general. Cool. So if we're trying to get A, and we already have V, AS, and we also have V inverse because we can just take the inverse of V to find out what the value is. So in order to find what A is, you just want to traverse another path along this graph that gets you from x to y. So something you can do is V inverse and then AS and then V. So you start up. And something to remember about matrix vector multiplication is that you always continuously left multiply. So the first operation that we want to do is V inverse. The next you want to do AS and then multiply by V. And then this will ultimately give you A times X. And this X is added in because earlier, in order to demonstrate the left multiply, I added the multiplication factor by the X vector. So this means that A is then equal to V AS times V inverse. And that is your final answer.